Okay, so let's make a start. So there's lecture 2 of this ST2334. We've left yesterday on chapter 1, page 42. And just a quick remembering what it is we were doing. So we were looking at the notions of probability, and basically through the notion of the set. So the idea is that we had an experiment where the kind of chance of something happening, this is the sample space S, the sample space, it's very exciting, and this constitutes all possible outcomes of some sort of random experiment, which for example could include rolling a dice or flipping a coin or something like that. And so what we had done for the duration of yesterday's lecture was to investigate events, that is subspaces of the state space. So you could take an event, this is A, and basically that would constitute something of interest which would happen, which may consist of a single point or multiple points, so simple being the case of a single point. Okay, and what we were doing at the end of yesterday's session was to look at operations on sets. So for example, we have a set A, we could have another set B, and we were investigating various operations on these sets, such as unions, i.e. essentially adding the elements together, intersection, the points which are in common, the notion of a complement, i.e. that you have a set, the complement being all points in the sample space which are not in the set, which is called a complement. And then we investigated a basic algebra associated with these operations, things like distributivity and De Morgan's laws, amongst other things. Okay, so we'd seen a lot of things yesterday. This is because it's just the introduction. And where we finished essentially was this example. So I'm just going to briefly visit this example. We saw it a little bit yesterday, just so that you have a full explanation to get you started with. So this example, so we looked at it yesterday. So it's this complicated scenario where you roll a dice, and if you get an even number, then basically you just flip one more time, and if you get an odd number, you flip twice. Okay, a coin. Okay. So basically in this situation you had, for example, all the possible outcomes. So this is the outcome where you roll a 1, that's an odd number, so then you have to flip the coin twice, and in this particular scenario, the one I'm highlighting, you flipped 2 heads in a row, and so on and so forth. And so in this example we were just investigating a couple of 3 events, A, B and C, which are listed in front of you. A, which says basically the event that the number on the die shown is less than 3. Okay, so we only roll once. So that's of course the scenario, all the cases where I roll a 1 or a 2. Okay, and this is all the cases. So I look in my sample space, here I rolled a 1, here I rolled a 1, here I rolled a 1, and so on and so forth. The set B is defined to be the collection of sample points for which 2 tails occur. And again, this is the same thing. I look here, I have 2 tails, here I have 2 tails, and so on and so forth. So there's 3 scenarios there. And C is the event that an even number is shown on the die. Okay, and so this is again the case where you get 2, 4, or 6, and that's pretty clear, as you can see below. So let's just have a look at a couple of these operations. We'd looked at this one yesterday, and it's a rather tiresome example. So we're just going to quickly look at what are we going to look at? Let's have a look at these couple of these operations just to finish off, because basically we've seen these multiple examples before. So this is something we didn't see yesterday. So here this is the example where I'm trying to compute the set A union B. Okay, so let's remind ourselves what is A and B. So A and B, sorry, we're going back to say this is A and B. So A union B is all the elements in A and all the elements in B. So I just basically take this set, I add these points to this set, and anything which is in common gets only 1 entry. So you can see here that the union is going to be this one, this one, this one, this one. This one's there, so I don't have to add it. This one isn't there, so I don't have to. I'll add it. This one isn't there, so I'll add it. So basically, as you can see, A union B looks like that. It's just a constituent of all those points. And you can check, so the complement of A and B, right, those things had been computed yesterday. They were these rather long and tiresome sets here. If you compute the intersection of those, i.e. the points which are in common between A complement and B, and then take the complement again, of course, by De Morgan's law, you get back A union B. Okay? And all the rest of these examples are essentially the same. I think you can work through those essentially because I'd like to get them move on. to some things more interesting. Okay, so this lecture, the main crux of this lecture is basically about counting methods. And why is this interesting? Well, basically this is interesting or of use in the context of probability and particularly experiments, because it allows us to work out, for example, the number of possible outcomes in an experiment. Okay, so we may have a combination of things that are happening, and we may want to work out how many possible things could happen. Okay, and we're going to see examples of that as we move through this section. And basically we're going to talk about that and scenarios where basically you can think about where two things are happening simultaneously, or either one or the other can happen, and how to work out how many things are going to ultimately be possible. Okay, and then towards the end of this lecture we're going to talk about things like permutations and combinations. Hopefully we'll get through that completely today. So the multiplication principle, so this is stated in two ways. I think that they're almost, well, they are equivalent because they mean the same thing, but I think this first one is the easiest way to think about things. So we're just trying to work out the following. So you have an operation being not necessarily a medical operation, something that could happen, and it could be performed in n1 possible ways. Okay, we're going to see examples of where that could happen. If for each of these two ways I have another operation which could happen in n2 possible ways, then the total number of outcomes of these pair of these operations happening is n1 times n2. Okay, so I have n1 things could happen, so that's maybe I can flip a coin and it could be head or tail, right? And then after that I might roll a dice. Okay, so the number of possible outcomes in this experiment is going to be the number of possible outcomes in my first experiment, which is flipping a coin, that's 2. And then I roll a dice, that got 6 possible outcomes. So the all possible outcomes of this experiment is going to be 2 times 6, 12. Okay, so that's one way of stating that. Maybe it's completely obvious, hopefully it is. It's an alternative statement, which, as I say, is equivalent. Okay, now this is a little bit more of a scientific statement. So suppose you have two experiments and you're going to perform them, right? Just as in my coin flipping and rolling of the dice. Experiment 1 can result in any one of n1 possible outcomes. So flipping a coin could be 2, head or tail. And if for each of those outcomes in experiment 1, okay, I'm essentially reading this, there are n2 possible outcomes of experiment 2, then, so in my example, that would be rolling a dice. Then the total number of possible outcomes is, of course, 2 times 6, or n1 times n2. Okay, so this statement here, whichever one you prefer, they mean the same thing. I think they're both equally transparent, although this one seems a bit more scientific on review. So let's have a look at an example. We're going to see a lot of examples, I think, for this. We're going to be, excuse me. Yeah, there's a lot of examples. Oh, there's only 2 examples. Okay. So the first one, so this is, I've even read the notes. So this first one is how many sample points are there in the sample space when you roll a die and you flip a coin? It's almost the same example as I was quoting, and that was by chance because I didn't read this before I came. So the 6 possible outcomes, 1, 2, 3, 4, 5, 6. I roll a die, I can get 6 outcomes, 6-sided dice in this case. And for each outcome, I flip a coin, and there are 2 possible outcomes, which is going to be a head or a tail. So as I was making the point, the sample space of this experiment has 12 points, okay? And basically here, one can characterize this sample space. S is the set of pairs X and Y. X belongs to the set 1 to 6, the integers from 1 to 6, and Y belongs to the set H or T, okay? And that has 12 points. Okay? Oh, okay, there's the answer. Sorry, I was jumping ahead, yes. So basically, as I say, the first operation has 6 outcomes, the second operation has 2 outcomes, so there's 12 possible outcomes in this experiment. Okay, good. So the second example is the following. So a community consists apparently of 10 people, 10 men in this case, and each of them has 3 sons. And so basically, one of the men is going to be chosen, along with one of his sons, to be the father and son of the year, apparently. The question is, how many possible outcomes are there in this scenario? I.e., how many possible winners could there be? Okay, so the first thing you have here is you're going to choose a father at some stage. So let's start with the father. So the father could be one of 10 possible fathers. So there's 10 possible fathers, and for every possible father, there's 3 sons. So that's 10 times 3 possible outcomes, 30 outcomes. Okay, so seems tedious, but this is going to become integral as we come on along towards the latter part of the lecture. So this is, I hope, not too difficult, but later on things will become more difficult, and this principle will become kind of something which is assumed that you understand from the beginning, hopefully. Okay, so a remark, and it's not a very complicated remark, which is you can generalize that to a sequence of more than 2 operations. So just like we looked at yesterday when we had the union of 2 events A and B, we talked about that finite or countable collection of unions, which is just a generalization to a union of n sets or / intersection if you do intersections. And you can do the same thing for this in the case when you have more than 2 experiments. I prefer the phrase experiments over operations. Okay, and it's not surprising what it's going to be. Okay, it's just a simple possible notion like this. So the idea is you're going to have 2 statements of this, right? 2 statements of this. Yeah. So let's do statement 1 and statement 2 are equivalent. It's basically just a generalization of the associated statement 1 and statement 2 of the first case when you only have 2 possible operations / experiments. So in this case, you're going to have k possible operations. So it says, the first bullet point says, if you have an operation which can be performed in n1 possible ways. Now, for each of these operations, you can perform a second operation, and that has n2 possible ways of occurring. And then for each of those 2, you have n3 for a third operation, and so on and so forth until you go to k. So the question that one asks oneself, you may want to ask oneself, and that's what we have to do sometimes in probability, is what are the total number of operations that could be performed, total number. And it's unsurprisingly n1 times n2 times ... times nk. Okay, so this just means I multiply these numbers, k numbers together. Okay. So as a quick example, so here I could roll 3 die, right? And I want to know what are the 3 possible outcomes, or what are the total number of possible outcomes, okay? So the first time I roll a die, I can get 1, 2, 3, 4, 5, 6. So there's n1 there. Okay, so then I'm going to roll again. There's another 6 possible outcomes. So I roll again, that's another 6. So that's 36 possible outcomes. And then I go roll again, and I get 6 to the power of 3 possible outcomes. Okay, so that's basically one way to think about it. The other one, which is the kind of notion which is an experiment, but an experiment or operation are basically exchangeable objects in this explanation. So now in this scenario, you have k experiments, and you're going to perform them. It's very important, by the way, this phraseology, right? It has to be that for every, so I do my experiment, I have n1 possible outcomes, right? It has to be that for each of those possible outcomes, when I perform my second experiment, I now have n2 possible outcomes for the second experiment, okay? And then so on and so forth. When I take my third, for those 2, after those 2 experiments, I have n3 possible outcomes for the third one. And so again, the total number of possible outcomes for these 3 or k experiments is the product n1 times n2 ... times nk. So the product of k numbers. And that's the number of possible outcomes. Okay, so again, those are 2 equivalent notions of the same problem. Okay, so let's have a look at an example. I kind of find this example a little bit funny because I don't know why you'd ever care about these things, but they are interesting from, I guess, a kind of number theoretic perspective. A number theory, not really at any level, but anyway. So the question is, or the example is, how many even 3-digit numbers can be formed from the digits 1, 2, 5, 6, and 9 if I can only use each digit once? Okay, so there are 3 experiments here. Okay, the 3 experiments are the number that I put in the hundreds, the number I put in the tens, and the number I put in the units, or the ones as we state here. Okay, now it does kind of matter which way you do it around, and the way in which one would do this particular type of problem is you think about what is the last digit in my 3-digit number. Why? Because that's going to determine whether or not my number is even or not. So remember, the even is in red, so I want to produce an even number. Now, if I want to produce an even number, if I have a 1 at the end, right, clearly that number is odd, so I can't use 1. I could use 2, okay, because that would bring me an even number. I can't use 5, that's going to give me an odd number. I can use 6, because that's going to give me an even, and of course I can't use 9, okay? So the answer to this first question, for the ones, or the units, that's the very final digit of this 3-digit number, I can only use 2 and 6, okay? So basically, at the first experiment, I can only got 2 choices. Now, once I've made that choice, I've got 2 or 6, no matter what I've got left, I can put that in the hundreds or the tens, doesn't matter which way I go, I'm going to produce an even number. So this is what this statement means. For tens and hundreds, I can use whatever is left. Okay, so my experiment 1, I don't like the way he's written it, it's gone 3 times 4 times 2. So my experiment 1 is 2. I have 2 choices, I choose a 2 or a 6. Now my next choice I have is, let's say, the tens, right? Now how many numbers have I got left? Well, I've got to have, basically I can choose any of the resulting four numbers left, and then I've used another one, so then I've got 3 numbers left. So I have 2 times 4 times 3. Okay? And that gives you 24 possible 3-digit numbers which can be even, which can be produced from this collection of numbers if I'm only using them once, and it's critical that I'm only using them once. If I have something else, if I don't have that, then there's something else. Okay, an example 2, so this one is a bit closer to our hearts. You have a test, it consists of 10 multiple choice questions. Each of them has 4 possible answers, okay, and we ask ourselves 2 questions. Let me see if they're repeated there. No. Okay, let's just look at A, we'll return to B, because if we think about what B is, we'll forget about what it is when we do the solution. So part A asks us the question, how many possible ways are there in which a student could choose to answer each one of the questions? So we have an MCQ, 10 multiple choice questions, and they have 4 answers, right? And you know, so there, of course, there are many possible answer booklets that could come out, right? But the total number of possible outcomes is what? That's what it's asking for. That's part A. So let's think about part A. So now I start, and I've got, so the key point of this example is to understand what are the experiments and what are the outcomes. Well, in this case, the experiments constitute the question, and the outcomes, or the possible outcomes, are the questions in which you answer, okay, i.e. one of the 4 multiple choices. So here, so if I start with my first experiment, I've got 4 possible outcomes, okay. Now I've done the first question, whether I'm right or wrong doesn't matter. The second question, now what have I got? Well, I got 4 possible answers, so that's 4 times 4. My third question, I've got 4 possible answers, that's 4 times 4 times 4. And then if I go all the way up to 10, I'm going to do 4 times 4 times ... times 4. That's going to be 10 times. So there's 4 to the power 10 possible answers or collection of answers which could be given to this test, irrespective of what's right or what's wrong. We're not worried about that. Okay, so now this question part B asks us, among all these possible cases, how many are such that their answers are all wrong, right? So of course, contained within part A, there's a scenario where I get all the answers right, a scenario I get 8 right, 9 right, 7 right, so on and so forth. And of course, there's a case where I get them all wrong. And the question is asking us, so we know that, for example, so just to say, so we know that the solution to B is strictly less than the answer to A. If I get more in B than I get in A, then there's a problem, okay? So now I'm answering the scenario, the subset of the answer in A, the subset of the test papers where I get everything wrong. I guess he's not really said it, but one is assuming that there's a unique answer for every question. But that's just nitpicking. So again, what is the experiment or the operation? The experiment or the operation is the question, and the outcome is now not just the answering of the question, but it's the answering of a wrong question. So for every question, one is assuming there's only one right answer, so there's 3 wrong answers. So in the first question, I have 3 possible outcomes where I get it wrong. Okay. My second question, I have 3 possible outcomes where I get it wrong. the third question, I have 3 possible outcomes where I get it wrong, and I have 10 questions. So I just do use my multiplication principle, or generalized multiplication principle. It's 3 times 3 times dot 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 3 to the power of 10. Okay, and that's 3 to the power of 10. It's good enough for me. I don't need to write out 59,049. You can if you like doing that, but 3 to the power of 10 is the answer, and it's good. Why is it good? Because at least I have a feeling that it should be right in some sense, because that's less than A. It is right in this particular scenario. Okay, example 3. We're beginning to get this one. This one is pretty much. This is actually easier than the previous one. So it's a college freshman, and this individual has to take a science, a humanity course, and a math course. And she can select one of 6 science courses, any 4 of humanities, and any 4 of mathematics. How many ways can she arrange her program? Okay. So again, here the operation is the choice. First, like doesn't matter which way you do it in this scenario, so I can do first humanities, then math, and then science. Okay, so in this situation, so if I start with science, I have 6 possible outcomes. Then if I do humanities, I have 4 possible outcomes. And then if I do math, I have 4 possible outcomes. So that's the answer is 6 times 4 times 4. Okay, it happens to be 96. Okay. Example 4. So example 4 is a little bit out of date because you can now fly direct from Singapore to San Francisco. But let's suppose you want to go from Singapore to San Francisco, and there are 4 airlines that actually do that. And for each airline, there are 3 possible routes. Okay, so there are still indirect routes there. Okay, so the question is, it doesn't. There's not actually a question there. Yeah, that's not a question actually, but the question is really asking us how many possible ways can you go to San Francisco as a combination of airline and route. Okay, so first of all, I choose my experiment, which is to first choose an airline. So I've got 4 possible choices. Okay, and then one conditional on my given my airline, now I have 3 possible routes I can choose. So there are 12 possible airlines/routes that I could take. Okay, that's really what that thing is. It's not a question. Oh, good. Okay, so we have another question. So this is now the 3-digit question again. So this is again something similar to, I think, maybe one of the first questions we look at. So it says, find the number of even 3-digit numbers which can form from 1, 2, 5, 6, 7, and 8. Okay, so it's very similar to the previous question, except we have 2 possible scenarios. Excuse me. The first possible scenario is if each digit could be used once and only once, and otherwise if there's no restriction on how many times I can use a digit. Okay, and again, the solution is very similar to the one we did before. Because the thing is that you have to first of all think about producing an even number. Okay, so to produce an even number, so what do we have? Remember, let's just remind ourselves. We have 1, so I put 1 at the end. Of course, I don't produce an even number. If I put 2, I do. If I put 5, I don't. If I put 6, I do. If I put 7, I don't. If I put 8, I do. Okay, and if you're lost track of what I'm saying, that's basically an explanation of this first sentence of this solution. Okay, right, so for each choice of those choice of ones is unit, if you'd like prefer unit, I now got 5 possible choices left in the hundreds. Okay, and then for each choice of the ones and the hundreds, you've got 6 minus 2, 4 choices for the tens. So basically the number of choices you have is going to be 3 times 5 times 4. Okay, if you do it in the order of this, or if you want, you can put it in numerical order, 5 times 4 times 3. Okay, and that's the solution 60, if you like. It's also good enough. Just to leave it as 5 times 4 times 3. Okay, part B. So part B is the same question, except now you're not allowed to, you can replace it. So if I choose 6, I can choose 6 again. Okay, and of course this again indicates that one should have a larger number of possible choices. You can see at the bottom the solution is 108, but how do we get that? Okay, so this is part B, yes. So again, if we choose the final unit, or the ones, again you have to put 2, 6, or 8 there. You've got no choice. Now, the key point is once you've chosen 2, 6, or 8 in the final position of the number, now I'm not doing any replacement, so I can basically choose any of the resulting numbers, and I choose them if I choose. So basically what it says now is that for each position I've chosen at 1, I can choose any of the resulting numbers which were left over. There's 6 numbers. So first of all, I got 3 choices. My second experiment, I got 6 choices. My third experiment, I got 6 choices. So in this case, you have 3 times 6 times 6 possible numbers that I could create which are even. The only constraint that has been imposed in part B is the fact that you have to produce an even number. Part A is slightly more complicated because I have to do it without replacement. Okay, and as I said, one expects from the nature of the question, the solution to part B has a higher absolute value, higher number than you would have in part A. Oh, goodness me. More of these in there. All right, so just 2 more to go through. The example 6 is pretty straightforward. This is easier. I don't know what the logic is of these questions, but anyway. So in this question, you have a set lunch. You can get some soup, you can get a sandwich, you can get a dessert, and you get a drink. Okay, and so those and for each of those, so basically we have 4 possible soups, 3 sandwiches, 5 desserts, and 4 drinks. And the question is, how many different set lunches can I have? Okay, this one is relatively more straightforward because basically the sequence of experiments or trials, if you like, soup, sandwich, dessert, and drink are clearly stated. Okay, so first of all, if I have a soup, well, I've got, of course, 4 choices. I get my sandwich, I have 3 choices. I get my dessert, I've got 5 choices. And I get my drink, which is 4 choices. I multiply them all together. That's what the bottom says. And apparently there is 240 different set lunches, so there's some variety there. Okay, all right, so this example, again, I don't like the phrasing of this question. It's kind of a little bit ambiguous, but it says, in how many ways can 4 boys and 5 girls sit in a row if the boys and girls must alternate? Okay, and it's kind of not very well stated in the sense that although it's implied that your row must start with a girl because there are more girls than boys. Okay, so it's maybe the thing to interpret here is because you have more girls than boys, you must start with a girl. Okay, so what's the solution of this? So the solution is that you must have, so again, this is what I was saying, so you must have the seat girl, boy, girl, boy, girl, boy, girl, boys. Feels like I'm still at school. But this is what you used to do at school in 30 years ago, maybe not now. So the question is how many possible combinations, how many possible ways there are of doing this. Okay, so first time out, well, we have to count how many girls and boys there are. So we know there are 5 girls, we know there are 4 boys. So first time out, I can choose any of the 5 girls, okay? So that gives me 5, okay? That's my first experiment. My second experiment, now I need to choose a boy. There are 4 boys, so I now have 4 choices. So I have that. So that's given my second trial, my second experiment. Now my third experiment, well, I have another girl, but in this case I've already chosen one from before, so I started with 5, I'm now down to 4 girls, so there are 4 possible outcomes. Okay, so that's the second 4 here. Okay, very good. And now we look at the next one, okay, and now I have a boy. Now the boy, I had 4, I've lost 1, so I've got now 3. So now I've got 3 possible choices of this boy, and that's what I have there. I'll do it one more time, I think you've got the point. The next one is the girl, the third choice of the girl. 2 girls have gone already, I had 5 to begin with, I've only got a choice of 3. So that's where I get the 3 from, and so on and forth, 2, 2, 1, 1, all the way to the end. And the answer, well, if you work it out, okay, you can get 5 times 4 times 3 times 2 times 1, and you can get 4 times 3 times 2 times 1, and it happens to be 5 factorial times 4 factorial. Now, if you don't know what factorial means, this is what it means, okay? So if I have a positive, so I have an integer which goes from 0, 1, 2 off to some number n, then the definition of n factorial is precisely n times n minus 1 times n minus 2 times ... and I go all the way to 1, except in the case where n is equal to 0. A 0 factorial is defined to be 1. Okay, so if you don't know that, you should write that down. It's mentioned later in the notes, but just in case you didn't know, I'll write it for you so you don't forget that. So 0 factorial 0 factorial, that's supposed to be a 0, nothing else, and it's defined to be equal, and defined to be equal looks like that, and that's the number 1. Okay, so 0 factorial is 1, make sure you please remember that. Okay, so this formula that's written here is true only in the case where n is 1, 2, 3, 4, 5, all the way off to anything. Well, let's say it's finite, otherwise we'll get some funny things. Okay, very good. So that's very important to understand this example, because we're going to go into some more complicated details as we go along. Let's have a look at something else. I think this one's easier to understand. I might have started with this one. It's much easier to understand. And it's called the addition principle. So now this is the following scenario. Again, it's similar and related and easier to understand, actually. Suppose you have a procedure. So again, we're going to have a collection of experiments. Okay, here we're calling them procedures. So I have a procedure, and I call it procedure 1. And that could be performed in n1 possible ways. Now I suppose I have a procedure 2, and that could be performed in n2 possible ways, but we make a constraint. So this addition principle has a constraint in them. So remember what we were saying before in the multiplication principle. I was doing experiment 1, and for every outcome in experiment 1, I have n1 outcomes, so experiment 2 has n2 as possible outcomes, so I have n1 times n2 possible outcomes. But both pairs can occur simultaneously, so any pair in experiment 1 and experiment 2 can occur. In this scenario, what we make the constraint is that it's not possible that both procedures 1 and 2 are performed together. So I can't do, for every outcome in procedure 1, experiment 1, I cannot get another corresponding outcome in procedure 2. So it's not possible that they're performed together. So then we ask the case, what are the possible ways in which we can perform 1 or 2? Okay, and that happens to be just the sum, right? Because I do experiment 1, I get n1 possible outcomes. Now, I can't do experiment 2, cannot happen at the same time. It's not possible that they both are performed together. So the total number of outcomes is n1 plus n2. Okay, and I think we're going to see a lot of examples, actually. So if it's not clear to you yet, you're going to see some nice examples in a moment. And this generalizes to the scenario where you have k procedures. You have k possible experiments, but they can't occur at the same time. Okay, and each experiment has n subscript I. So this is ni as a number between, I guess it goes from 0 off to any non-zero, any finite integer. So ni is a number which can happen, is a number of possible things can happen in the ith experiment. Okay, so then basically the way in which we may perform procedure 1 or 2 or ... or k is just the sum. It's the sum I is 1 to k of the ni's, or if you prefer, n1 plus n2 plus ... plus nk. And this is assumed, but the constraint is that no two procedures can be performed together, because if they can, this is obviously not the answer. Okay, let's see an example. It's actually hard to envisage an example where this may be happening, but here's an example. Again, it's not a very, it's a kind of murky example, but anyway. So you can take, for example, the MRT or the bus. You can't take them both. Apparently, of course you can, but let's suppose you're loyal to one or the other. I'm either going to take the MRT and I stick with it, or I'm going to take the bus. I'm going to stick with it, and I want to go from where I live to Orchard Road. Okay, and we're told there are 3 bus routes and 2 MRT routes. Then what's the total number of routes that I could take? Okay, so I'm either going to choose the MRT or the bus. I'm not going to choose them both. I'm not going to mix and match or anything like that. So the total number of routes, if I stick to this dogma of basically choosing the MRT or the bus, there's going to be 5 possible routes I can take, because basically I choose the MRT and then I've got 3 things I could do, and if I choose the bus, I've got 3 routes, and if I choose the MRT, I've got 2. So there's 5 different routes I could take, and this is an example where they cannot occur simultaneously. Of course, this is a kind of funny example because they could not occur simultaneously. Okay. So example 2, I think example 2 this one's a nice, at least once we've got used to these questions, we kind of do them, at least this one, it becomes more interesting. So the example 2, so we're back to our favorite question. We want to work out, we want to know how many even 3-digit numbers can be formed from 0, 1, 2, 5, 6, and 9 if I only use each digit only once. Okay, so there are two cases. Well, I think this is one of the easiest ways to think of this question, and it helps helps us to understand this addition principle. There's not necessarily a unique way of doing it, but I think this is the easiest way to think about this. So we think about these two cases, and we think about the special case 0. So why do we do this in this way? Well, if you think about the way in which we try to solve these problems so far, what we do is we try to think about the final digit of our 3-digit number and the constraints that places upon our resulting experiments. So we're going to do it in the same way in this scenario, but we start with the case where we just consider 0 being in the unit, or the ones as we were using that phrase before, because 0 is a special number, because I can't put that at the front of my 3-digit number, right? 0, 1, so if I put 0, 1, 2, that's not we don't count that as 12, that's not a number. So I can only put 0 in the ones or the tens. So I think about putting 0 at the end first, because I know if I put 0 at the end first, that number, the results, that 3-digit number is always going to be even, okay? So, if I use 0 for the ones, okay, then it doesn't really matter what I do for the resulting other two. So I can use 1, 2, 5, 6, or 9. Doesn't matter in the tens and the numbers that left over for the hundreds, and I'll get an even number. So the number of possible ways in this scenario is that I have 5 times 4 possible ways to arrange the hundreds and the tens. So in this scenario where I choose 0 in the final position, I have 20 possible ways to create such a number. Now, of course, that's not exhausted the possibilities, because I made a constraint here. The constraint is I put 0 in the final position. So another scenario, which is that 0 is not used in the ones. Now, this is a more clear example, because basically I can't use 0. If I put 0 at the end, and I don't put 0 at the end, these are two scenarios which cannot occur simultaneously. So they are kind of disjoint type scenario. Okay, so now if I don't use 0 at the end, what have I got left? I've got 1, 2, 5, 6, and 9. Okay, now if I do that, now again, I start at the ones or the last unit. Well, if I put 1, 5, or 9 at the end, I get an odd number. So I must use 2 or 6 at the final unit. Okay, now let's deal with the hundreds. Why do we deal with the hundreds? Well, basically because I can't put 0 at the front, as I said. Okay, so once I've chosen either 2 or 6, I can only choose basically 1, 5, or 9, I think. So 4 possible choices, yes, sorry. There are 1, 5, or 9, or the other one, right? So if I choose a 2, I could choose the 4 the next time around. So in the hundreds, I have 4 possible outcomes. Okay, so there's 2 times 4, and then basically whatever is, then after that I can put whatever I like in, okay, and there are 4 choices left over after that. So that's 4 times 4 times 2, so that's 32, okay. But that's still not the solution, because in order to get the solution, the total number of ways is then the case A plus case B, which is 20 plus 32. So that's the total number of even digit numbers in this particular example, and it's slightly more complicated because I have to think about 0. That's the thing that makes it marginally more challenging. Okay, all right. So now we're going to do. So this one actually takes quite a while. It will basically take us up to our break, I think. So example 3. So we consider the digits 0, 1, 2, 3, 4, 5, and 6. Okay. Right, and there's a B as well, isn't there? Goodness me. So let's do part A. So part A says the following. I'm only ever allowed to use each digit once, and I'm asked part 1, how many 3-digit numbers are even, and how many of these is greater than 420? Okay. So that's the question. We'll look at B in a moment because we're going to forget what B is if we ever get there. Okay, so let's look at our numbers. We have 0, 1, 2, 3, 4, 5, and 6. So part 1, we've already done something. That was the last question, essentially, except with different numbers. Because we have the case, we have 0 in our cohort, so of course we cannot consider that. So we consider that with the disjoint case. So part 1, so case 1, we look at the case where the last digit is 0. Okay? Now, basically, after I've done that, I can do whatever I like because I'm going to produce an even number. So then I have 6 and 5 choices left over. There's 7 numbers, right? Okay, there's 7 numbers. So I've chosen 0. It's at the end. And then basically, I've got 6 times 5 choices left over. So that's 30. So that's case 1. Okay, this is just a rehash of the previous question. Case 2, the number of 3-digit even numbers with the last digit which is other than 0. So if that's not the case, now what have I got? I've got the choice of 2, 4, and 6. So I have 3 choices like that, and then basically I'm subtracting 1 every time after I do it. So I first of all have 3, then I have 5, and then I have 5. Okay. All right, because 3, I've used 1, I've used 1 again. Okay. So apparently that's 75. So the scenario, of course, the solution is exactly the sum, the addition. So the first thing we did, we used the multiplication principle in case 1 and case 2, and now we use the addition principle to get the solution to A part 1. It's just 30 plus 75, apparently. Okay, now let's remind ourselves now. We want to do part A part 2. So that says I can use each digit once, and I have to work out how many of those are greater than 420. Okay, so here we are. Okay, so let's have a look at this. So this scenario is going to be the case where the hundreds is 4 and the tens is 2. Okay, so now I have to think about that. So that's one choice in 100, one choice in tens. So that's going to be 420 something. Now I want to be, so the question says strictly bigger. What does it say? It says how many of these are greater than 420, and I've already chosen 4 and 2. So what have I got left over? I've got 1, 2, 3, 4, 5 numbers, but of course I can't use 400. I can't use 0. So that means, oops, sorry. Sorry, here we are. So basically now I have 4 choices left over. Okay. So basically, because I can only choose, so what the 1, again, it comes from here, the 1 comes from here. This one, I have eliminated 2 numbers already. I had 7 numbers, I believe, and I can't use 0 because it says it's greater than, not greater than or equal to. Okay, very good. So that's case 1. Case 2, let's take the hundreds as 4. Okay, so I have to take the hundreds at least 4, otherwise there's never going to get an answer, right? I have to take 4. So if I do that, now if I take the hundreds as 4 and I take the tens, after that I have to take the tens as 3, 5, or 6. Okay, I can't take the tens as 4 because I've already chosen the hundreds as 4. Okay, and the only case where I'm going to be bigger than 420 now is if I have a 430, 450, 460. So after that, so then I can choose tens, so I have 1 choice here, I have 3 choices here. Now I've chosen 2, and I can choose whatever I like here, so I have 5. Okay, so it's 5, not 4, because basically I can choose whatever's left. Okay, case 3, well, if I take hundreds as 5 or 6, okay, so if I take 5 or 6, obviously I'm going to have 500 something, 600 something, that's great. So after I've chosen 5 or 6, well, it doesn't matter what I do here, right? Because I can choose all of the numbers left. I've only chosen 1 at this stage. So I've chosen 1, so I've got 6 left over. I've chosen 2, I've got 5 left over. So I have 2 times 6 times 5. This is supposed to be multiplying these things together. If you're wondering, this is not 114 and multiplying these things together. Okay, so those are my 3 cases. Do I have any more left? I don't think so. So then basically the solution is if I have case 1 or case 2 or case 3. So I'm going to add these 3 numbers together, which is 4, 15, and 60, and the answer to that is 79. Okay, so let's do part B. Our break is coming, but let's do part B, otherwise we come back and we won't forget what we were doing. Okay, let's just do part B. So part B now is the same kind of set of numbers. So I have 7 numbers starting with 0 and going up all the way to 6 in units of 1. And I'm asked 3 questions. So the first one is how many, the key point here now, so it's in red, you can use each number more than once, okay? So it's not like if I take it out, I have to, if I take it out, I replace it, okay? In the previous example, I didn't replace it. So my first question is, how many 3-digit numbers can be formed, okay? And this is relatively straightforward because, again, I know I can't put 0 at the front, but other than that, I don't have many constraints. So this one's pretty B part 1. So there's 6 choices. So the way I work it out here, I'm not got any. It's not even. It's just how many numbers, right? So at the position at hundreds, well, I can choose 1, 2, 3, 4, 5, 6. I can't choose 0, as we know already. So I have 6 choices at the first position. Now, at the next position, I can choose any of the 7, and the next position after that, I can choose any of the 7. So the solution to this question is going to be 6 times 7 times 7. That happens to be 294. Okay. In this scenario, it's a little bit easier because basically we don't have any constraints. Okay. Now, this is getting a little bit more tricky. B part 2. How many 3-digit numbers formed are odd, and how many are even? Okay, so now this is getting a little bit more complicated, but again, it's really all about thinking about that last number. So again, so the 3-digit odd number. Okay, so in this case, again, I can only put, I think about the last unit, the ones, as it's written in the notes, and of course I have the choice of 1. I can't choose, if I choose 0, I don't get anything. If I choose 1, I get an odd number. If I choose 3, I get an odd number. If I choose 5, I get an odd number. And any of the other choices doesn't give me anything. So first of all, in the ones position, I have 3 choices. Now again, in the 100 positions, I'm not doing any replacements, so I could potentially choose them all, but again, I can't choose 0. So I have 6 choices, and then in the tens position, I have 7 choices. So the total number of odd numbers that could be produced in the way stated is going to be 3 times 6 times 7, which is 126. Okay? And now the same thing for the even number. The even number is pretty straightforward. In the even case, because there's no replacement, we don't have to break things up here. Before we have replacement, and so when we take something out, it becomes more complicated to think about. Here, there's no replacement. So in the case of the even number, again, we start at the ones, or the digits at the end. So I could choose 0, 2, 4, or 6, okay? And because I can replace them, the scenario is going to be the same afterwards. So basically, that's 4 choices there. Okay. Now in the hundreds, of course, I have 6 possible choices. I can choose 1, 2, 3, 4, 5, 6, and in the tens, I can choose any of the numbers. So that's 7. So that's 4 times 7 times 6. Okay. Very good. So now part 3. So I'll spare you. I won't spare you. I will go through part 3. Oh, sorry. This is. Oh, okay. So this is very similar to A part 2, except. You have the case of replacement, no replacement. So it says how many 3-digit numbers formed are greater than 420. Okay. So again, this is going to use the addition and the multiplication principle. Okay, so we take this first of all. So of course we know that the hundreds have to be at least 4. So they're going to be 4, 5, or 6. You can see that in case 1, 2, and 3. So we think about case 1 where I put hundreds in 4. I put 2 in the tens, so I get 420 something, and then what's left over? Well, I can choose anything apart from 0, so I have 6 choices in this case. So I have 1 choice, 6 choices. So that's 6 cases when I first a 4, then a 2. Case 2, I take 4, but now I take any of these 3, 4, 5, or 6. Okay, doesn't matter which. Okay, then basically once I've chosen 4, I have 1 choice here. These are 4 numbers here, and the last one I can put whatever I like because I'm 430 something, 440 something, 450 something, so on and so forth. So I can choose what I like here. So there's 1 times 4 times 7. And the case of 5 or 6, well, if I choose 5 or 6, I have 2 choices. And once I've chosen 5 or 6, it really doesn't matter what I do. So I can choose a 7 here, I choose a 7 here, and I'm, of course, immediately above 520. So that's 98. So I'm just going to add these numbers together, I guess. And that is the number of possible numbers that I can form of 3 digits without replace from 0, 1, 2, 3, 4, 5, 6. It's 132. Okay, very good. So we're going to break for 5 minutes. That takes us to 14:54 on the red clock, and we'll resume after that. Thank you. Okay, so let's resume. So we've moved on now to this section 1.3.3. It's page 81 of chapter 1, part 1, and it's all about permutations. So permutations. In fact, there's one key slide in a couple of slides' time. If you understand that, you'll understand the whole part of the permutations, and I'll mention which part it is when we get there. What is a permutation? We may know already. Basically, if you have n objects and you choose r of them, it's an arrangement of r objects from n, and the order is taken into consideration. Okay. What does that mean? If it doesn't make any sense to you, let's see an example, because it will make it very, very clear. So now suppose that my number of things n is a, b, and c. And I have 3 things, and I pick 3 of them, and I want to know the number of ways I can arrange a, b, and c. Okay, and you can see the 6 cases: a times a, b, and c, a, c, b, a, b, a, c, b, c, a, c, a, b, c, b, a. Okay, so that's what it meant by permutation. In this example, n is 3, r is 3. Okay, very exciting. Let's try and understand this. How do I know it was 6? It wasn't magic. There's a formula for that. Okay, so there are 3 choices. How do I know that there are 6 possible outcomes? Well, the way it works is the following, and it's just basically following from this multiplication principle, where basically my first experiment is I can choose any of A, B, or C. So I have 3 choices. Okay. Now, my second experiment is now choosing the resulting 2 that left over. So now I have 2 choices, so that's 3 times 2. And at the end, I only have 1 choice, and so that's 1. So the number of possible outcomes in this experiment is 3 times 2 times 1, and it exactly corresponds to the number of permutations of 3 objects, the number of ways I can pick 3 from 3 items and arrange them in any possible order. Okay, so that's why I get 3. And in general, if you take n things from n, it's n factorial, and that's what you get from that. So why is that the case? So let's think about this. Now I have n items, and I'm going to choose n from them without replacement, and I want to know how many ways I can arrange them. And it happens to be n factorial. Why? Okay, so let's think about this in our multiplication principle perspective. So first of all, I want to choose one of the n items, and I can choose any of them. So I have n possible outcomes. Okay, that's experiment 1 done. Now, I've taken that first item out, whatever it was, and I'm left with n minus 1 items, and I'm going to choose any one of those. So my second experiment is the choice of any of one of n minus 1 resulting items. Okay, I go to my third experiment. I've already used 2 of my items, whatever they are. I have n minus 2 left, and I'm going to choose any one of those. So I have n minus 2. And I keep on doing that. I have n minus 3, and all the way until I get down to 1. Okay, and so by definition, n factorial is n times n minus 1 times dot 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 times 1. And so basically the way of choosing n things from n items, the number of permutations that you can get is precisely n factorial. And of course, n is typically at least 1, so we don't care about the case 0, but as I told you earlier, 0 factorial is defined to be 1. 1 factorial is defined to be 1, of course. The product on the left-hand side is strictly 1 in the case n is 1. Okay, so that is the number of possible ways you can choose n from n. Okay, that's not exactly what the notion of a permutation was. So what we want to do, what we said, we defined a permutation is I have n items and I take r of them, and I want to know the number of ways I can take r from n. What are the number of possible permutations? Okay. And basically this is the slide. If you can understand this slide, then the rest of this permutations part makes sense. Now the formula is given to you like right here. Okay, n factorial over n minus r factorial. Now the question is, why does that make sense? And the easiest way to think about it, is this explanation here. So now what I'm going to do, so I want to take r out of n. R is at most n. Okay, my example previously is the case where I take n from n from n. Okay, but here I'm taking r. R could be 1, 2, all the way up to n. Of course, I don't take r as 0. It's a silly question. So the first thing I do, so I have n items. I choose the first one, and that's I have n choices. Okay, that's my first experiment. Experiment 2, right? I'm going to choose another one. I've already chosen one. I've got n minus 1 possible choices, so there's n minus 1 possible outcomes. Okay, so I have n times n minus possible choices, n times n minus 1 possible ways so far. The second way, I've now chosen 2, and I want to choose my third item. So I've chosen 2, so I've got n minus 2 possible outcomes, and so on and so forth until I get down to my r minus first choice. Okay, and my r minus first choice, I've got n minus r minus 1. Sorry, my rth choice. This is my rth choice. My first, this is 1, this is 2, dot, dot, dot. This is my rth choice. And I have n minus r minus 1 possible choices, possible outcomes. So that's basically the number of possible ways of permutation of choosing r from n. Okay? And it so happens that this product, which is n times n minus 1 times dot, dot, dot times n minus r minus 1, is exactly equal to n factorial over n minus r factorial. Okay, so this is why this formula is the one that's quoted, but this is the easiest one to understand of why it is like that. Okay, and if you understand the formula here, there's going to be a case where you have something slightly more complicated. It's going to look horrible, but it's exactly the same formula. Okay, this is the one has to understand. Okay, so if you're wondering why is this the case, n factorial over n minus r factorial, well, if you don't, let me just tell you, just in case you didn't know this, I'm sure you can do that calculation yourself, but basically, that on the top you have n factorial over n minus, oh, good God, n, what is going on with this? No, let me start again. No, why did they create technology? Okay, right, sorry about that. Okay. So n factorial over n minus r factorial, just in case you're wondering, that's n times n minus 1 times dot 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 times 1 over n minus r times n minus r minus 1 times dot 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 times 1. So basically now, if you can read it, you probably can't read it, but basically the point is that the numerator that I've written down here is n times n minus 1 times dot 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 times 1. That's n factorial. The denominator is n minus r times n minus r minus 1 times dot 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 times 1. Then if you cancel, don't forget that r is at most n, so if you cancel the common terms between the numerator and the denominator, that will precisely give you the formula which we write here, which is n times n minus 1 times dot 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 times n minus r minus 1. Okay, so this formula here, which is the one that was particularly typically quoted, is precisely equal to this one here, where I think that the line which I've highlighted, excuse me, this blue line, is the easiest one to understand from a kind of intuition perspective. Okay, and if you understand this equation, you're going to see another equation in a minute where you have k possible things out of n is going to look horrible. It's this same formula. Okay. All right, let's have a look at examples. Yeah, we've already done that. I don't know why that's just going to slide. Let's have a look at some examples. Okay, so now let's says the following. Says find the number of all possible 4-letter code words in which all letters are different. Okay, so I have in this scenario 26 possible letters. It's English alphabet, I suppose. So I have 26 letters and I have a 4-letter word, code word. So I have a choice of 4 of those. So the number of possible code words of length 4 that I could choose is, of course, 26 factorial over 26 minus 4 factorial. It's just precisely, we don't care about the order, right? You know, X, Y, Z, A is different from A, X, Y, Z, for example. Okay, we don't care about the order, we count those as 2 distinct words. Okay, and so that's 26 factorial over 26 minus 4 factorial. Well, of course, that is just 26 factorial over 22 factorial. Okay, and you don't know, and then of course you cancel, so it's 26 times 25 times 24 times 23. And in fact, for me, I'm actually a mathematician, so I would stop there. If you want, you can use your calculator and get 358,800. I'm actually happy with this. But of course, that's just me. Okay, example 2. So I have 20 horses in a race. Okay, how many possible ways are there to arrange the first, second, and third place? Okay, so horse 1 could finish first, horse 2 could finish second, horse 3 could finish third, and so on and so forth. So this you already know the answer. Actually, you know that n is 20 and r is 3, right? So that's what you have. 20 horses, the first 3 places, there are 3 places, so that's 20 factorial over 20 minus 3 factorial, so that's 20 factorial over 17 factorial is 20 times 19 times 18, okay? And so that happens to be 6,840. Okay, so this one is a little bit more complicated. One has to think a little bit more, but I think it's worth doing. So let's have a look. So we'll start with part A. It's all about people lining up to get on a bus. So this one says, how many ways can 6 people, this is 6 people, not 6 persons, 6 people line up to get on a bus? Okay, this one's not so bad. So what's the answer to that? Let's put this question up here. So there are 6 people, and I'm going to choose 6 of them. So this is the case where n and r are equal, so that's n factorial, 6 factorial. Okay, that's the first thing that we said before. Okay, 6 factorial. You can use the formula 6 factorial over 0 factorial is 6 factorial by definition. Okay, now part B is more complicated. Part B says the following. If 3 certain people insist on following each other, how many ways can 6 people line up? So now this is more complicated because you've got these 3 people who are being very unpleasant and saying, I'm only lining up behind him or her. How many possible lines can I get? So the good thing, so the thing here, you know. Okay, so hopefully this will last for the rest of the session. They're actually not new batteries, but sorry about that. So this question is a little bit more challenging because, as I said, you have these 3 people who can only line up behind each other. So how can you approach this question? So again, this is the solution we look at, but it need not be the way you do it. Okay, it's just one way to formulate the solution to this problem, and I think that's an important thing in kind of science in general. Often there is not just one solution to the problem. This is the way we choose to do it, and you can do it this way. If you have an alternative solution, it's also fine, so long as the answer ends to be the same in this case. So here what we say is we suppose we have individuals, and we'll call them A, B, C, D, and F. Okay, and we'll suppose A, B, and C are our trouble people that they'll only queue behind each other. Okay, so now let's just basically denote that group A, B, C as this set capital A. Okay, so now what I have is I have 4 objects, right? So I can order these any way I like, right? So that's 4 factorial possible ways of arranging them. Okay, so that's 24, but I'm not done yet because in my formulation here, this ordering of A, B, and C has not been taken into account. So now, basically, for each of those possible 24 cases, within them, I have to now order those 3 individuals who are only going to queue or are going to be queuing together. And of course, the way in which I can arrange A, B, and C is 3 factorial. So in this case, basically, the solution to the question is going to be 6, which is the number of ways those 3 trouble people can be arranged, multiplied by 24, which is the number of ways that I can arrange those 4 blocks together. And so there's 144. The solution is kind of a little bit reassuring because, of course, that's less than part A, I think. So 720 is what I got in part A. Now, part C is a little bit more complicated. It says now, if two people refuse to follow each other, then how many ways can we line up? Okay, so now we have so before we had 3 had to stick together, now we have 2, then they're not going to allow to stand next to each other, maybe they have an argument or something. Okay, so first of all, find the number of ways to line up with these 2 people when they follow each other, and then we're going to take the complement. So similar to the part B, the number of ways to line up with these number of people is going to be together is 240. So what is this? How do I get this 5 factorial and 2 factorial? So what I'm doing here is I'm repeating the solution to part B, except instead of having 3 problem people, I have 2 problem people. Okay, so let me just repeat what did I do in part B. So in here, what I do is I have 2 factorial, and in here I have 5 factorial, because I have now the objects A, B, and then I have C, D, and F. Okay, so I have 5 factorial. So basically that means that this is going to be 5 factorial times 2 factorial. Now, of course, that's not my answer, because that tells you how many times I can line up with them in, with having those 2 people together, but that's not what I want to do. But the good thing is I do know now the number of scenarios where they are queuing together, and I also know the total number of possible queues I can have. So what do I do? Well, I just take the total number, 720, and I take away 240, and that basically this is the complement, if you like, which is 480 possible lines that you could have, or permutations, excuse me, in this scenario we're only allowing, we're not allowing 2 particular people to line up next to each other. Okay. That is, of course, not the only way. It's not a very constructive way of doing it, but I think it's, again, given one had done the problem in the case B, excuse me, that gave you a nice way to solve part C. Okay. Yeah. All right, let's do this. I mean, just for the sake of argument, but let's have a look at this. This one is the case. So here is a permutation of n distinct objects which are arranged in a circle. So this is the example. I have A, B, C, and D. And basically, this is the number of, I'm asked, how can I arrange those n objects in a circle? Okay. And that's n minus 1 factorial. Okay, I'm giving you the answer. Why is that the case? Well, let's think about that. So what you do is you consider a person fixed, and then basically you have n minus 1 people left over, and so there are n minus 1 factorial possible ways of arranging them. Okay, and so that's why you get n minus 1 factorial, not n factorial. It's in a circle. Okay, if you don't understand it, the way to think about it is you just take, I would say 4 is a bit too many, you just take 3, and you try and do this exercise, and you'll get n minus 1 factorial. And of course, that if that's the case with 3, you can generalize that to the more general case. Okay, so this is the question. So this is a question. It's basically the only question one could ask almost. How many different arrangements are possible for 4 people sitting around a table? It's a round table, otherwise it doesn't make any sense, right? So you have a circle. Okay, we know the answer because that's 4 minus 1 factorial, 3 factorial, which is 6. Okay, this is just a remark. I guess it's a remark more than anything else. I guess they probably will see something similar in the problems classes. Okay. So now we get something more complicated, and it looks really much more difficult. You look at the formula, even if you haven't read this slide or haven't said anything about it, it looks horrible. But the thing that I want to say about this slide is it's essentially identical to the one that I told you beforehand. So of course I'm going to explain what this slide is, but remember this slide. Oh, there you're going to, this one, okay? The formula that we're about to investigate is exactly the one that you see. I'm pointing at it, it's not giving you a lot of help. It's essentially exactly this type of formula. Almost exactly. Okay. Okay, where do we get? We get there in the end. Okay. So this says the following. So what's the case? Okay, so I'm trying to give you the intuition. So the case is you have n objects. Okay. But there are each object is of a different type, so there are k different types of objects. Okay, so and of those k objects, there are n1 of type 1, n2 of object type 2, n3 of object type 3, and so on and so forth, and their sum equals n. Okay. So what do I mean? So for example, you could take a hat. I've got 3 blue balls, 3 red balls, and 7 green balls. Okay, that's what you mean by that. It's a strange example. And we're asked the question, what the number of distinct permutations of these objects taken together is given by this formula here. Okay, and it's very similar to the one we had before, n factorial over n1 factorial, n2 factorial, nk factorial. So basically, if you recall, so again, let's try and think about this. Why does this make any sense? There's no explanation in the notes, actually. It doesn't help you a lot. But you can think about it in a very similar way to this. So in this scenario, I had n objects, I had r objects, and I'm choosing r from n. So very, very briefly, basically, the numerator is the total number of objects factorial, right? And that's exactly what we have. N factorial we have in our new formula, except n factorial is n1 plus n2 plus dot dot plus nk. N minus r is like the total number minus r. And this is very similar to what we have. We have basically the number of ways you can order the first one, n1 factorial, the number of ways I can order the second one, n2 factorial, the number of ways I can order the third one, n3 factorial, and so on and so forth. There's a nice parallel between this formula. It's not exactly the same, of course, because it's not exactly the same thing. But basically, the intuition is that this denominator roughly corresponds to the denominator that you got in the other case, and so does the numerator. It's almost the same formula. Okay, but basically, so just keep in mind, what does this formula mean? So it's the number of distinct permutations of these n objects taken all together. Okay. Okay, let's have a look at an example. So this is, it's very similar to the one you have here. So here you have 3 red, 4 yellow, and 2 blue bulbs arranged in a Christmas tree lights with 9 sockets. So how many ways? Okay, so in this case you have 9 objects. Okay, 3 plus 4 plus 2 objects. So n is 9. I think this one is not so useful actually. And basically the number of type 1, we'll call that type 1 red, type 2 is yellow, and type 3 is blue. And n1 is 3, n2 is 4, and n3 is 2. So the total number of distinct light arrangements is, you just substitute in the formula, you sum these out, they get 9 factorial, I get 3 factorial, I get 4 factorial, and I get 2 factorial. Of course, it's not a very useful example. If you want to understand the formula, you could basically take n1 is 2 and n2 is 2, and then think about what you would get in practice. I think that's the way to think about it. This long, you've only got 1260, is very hard to understand why that would be the case if you don't understand the formula from the beginning. Example 2. Okay, example, this is just, we're just substituting numbers into formula. I'm not sure how this helps, but anyway. So you have 4 math books, 3 physics books, and 5 chemistry books, okay? And how can you arrange them? How many ways can you arrange them if you don't care which is next to which? Okay, so how many books are there? Well, there's 4 plus 3 plus 5. Okay, so that's 12. Okay, and there's 4 math, 3 physics, and 5 chemistry. So the total number of permutations, in the sense that we said before, is going to be 12 factorial over 4 factorial and divided by 3 factorial divided by 5 factorial, i.e. in the formula is written there. And that's enough, okay? If you want, you can work that out as 27,720, but this formula is exact, so I'm okay with that. You can put the right-hand side with it, it's okay. Example 3. So example 3, so sorry, these are all repetitive, unfortunately. So here you have 7 people, and okay, this one at least you have to think a bit. So you have 7 people, and they have to be assigned to a triple and 2 double rooms. Okay, so note that you've got 7 people here, and the rooms, you can hold 7 people in them. Assuming that the double rooms are different, okay, so then the question is, how many ways can you arrange them, okay? So there are 7 people, n is 7. So there's 1 group of 3 people, 2 groups of 2 people. Okay, so I have n1 is 3, n2 is 2, and n3 is 2. So this sentence here is supposed to mean that the two rooms are different. So I have three different types of rooms, even though the last two rooms are of the same capacity. And so then, of course, then the answer is, because we're doing this thing, 7 factorial over 3 factorial, 2 factorial. Okay. Very good. Okay, so good. So we're going to get into combinations. So combinations, we're going a little bit fast. We need these things, actually. Combinations and permutations are very important. Spot combinations are important because they form a critical part in some of probabilistic problems, in fact, sort of permutations. So permutations are almost the same thing as, combinations are almost the same thing as permutations. The difference is, in permutations, we don't care about the ordering, okay? But in combinations, we do. So, for example, what do I mean by that? What am I talking about? Well, let's go in our very first example of permutations. If you'd forgotten, this is you have A, B, C, and I want to choose those three things, and I'm interested in a number of possible ways I can do that. Okay, well, I have this here. So this is the number of possible orderings that I have, right? But in combinations, I'm not interested in the ordering. I'm interested, so if I have three things, and I want to choose three things from three things, and I don't care about the order, there's only one thing I can do. I choose A, B, and C. Okay, so it's not the same thing. So permutations, the number of permutations, so if I take permutations, so I take R objects from n things and I don't care about the ordering, that's permutations, and that number is always at least, if not bigger, almost always bigger than the number of associated combinations. So I don't care about the orders. And so that's called combination, as I said. So again, you have n things, I choose R of them, and I don't care the permutation. Okay, so if I have A, B, and C, and I choose two things, I can choose an A and a B, I can choose an A and a C, and I can choose a B and a C. Okay, so there's only three ways of doing that. But of course, the number of permutations we know is 3 factorial over 2 factorial. Okay. So how do you get this? So there's a formula for working that. So just as we said before, the number of permutations is of choosing R from n is n factorial over R factorial. The number of combinations also has a formula. Okay, we're going to explain this. I'm going to explain this sentence in a moment. And it's called n choose R. It's called the binomial coefficient. And it has a particular formula. Okay, and where does it come from? So this bullet point attempts to explain it. We're going to explain it in more detail in a moment. A combination creates a partition with two groups. One group contains the R items, R objects selected, and the other one is constrained or contains the n minus R objects left over. Okay, and so it's said that the total number of combinations is n choose R, and we're going to explain first of all what that formula means. If you don't know what this thing actually means, this is a meaningless statement, but we're going to write down what that is, and I'm going to explain to you what that is. So the formula, and then we're going to explain the intuition behind it in a moment. So the number of combinations of n distinct objects taken R at a time is denoted n choose R. So n choose R is this left-hand side. That's what I'm saying, n choose R. But it has the mathematical formula that the right-hand side is specifically n factorial over R factorial multiplied by n minus R factorial. Okay. And so that is the number of combinations. So again, I have three objects. I choose two of them. I'm interested in a number of possible ways. I can take 2 from 3 where I don't care about the ordering, and it happens to be 3 choose 2. Okay. Now, where does that formula come from? It's mystifying in some level. So let's understand, where do we get the formula from? Right, so to develop the formula, let us derive the following example. So now let's look at permutations. So permutations we understand. So I take 4 letters, A, B, C, D, and I take them 3 at a time. So I know how many permutations there are of A, B, and C and D when I take 3 of those 4. That's 4 factorial divided by 3 factorial, which happens to be, n factorial over n minus R factorial is 4 factorial divided by n minus R factorial, which is 4 minus 3, 1 factorial. So I have 4 factorial on the top, that's 16. Okay, so that's 16 possible permutations, and they're all written down for you. Okay, that's all my 16 permutations. It doesn't look very exciting and it's not supposed to be, but hopefully if you've forgotten what a permutation is, that's what it is. Now, these are the permutations, but I don't care about that in combinations. I only care about the ones which are distinct, but not the ordering. So now if I look at this first row, okay, the first row which is going horizontally along the page, all of these row takes A, B, and C from A, B, C, and D. Now, of course, the ordering of A, B, and C is different across the row, but they all take A, B, and C. So the permutation cares about this. So I get 6 as a number of a contribution to my permutations, but for my combination, I only get this one. Okay, and simultaneously, and so of course that's the same across this matrix, ABD. So I choose ABD. So of course these are the 6 possible ways I can choose ABD, but for combinations I only care about this one, and similarly this one, and similarly this one. Okay, very good. So how does that help us explain or understand how do we get those formula? How do we get that formula n choose r? So of course the n choose r, so before I go any further, of course intrinsically, so just looking at this formula before I say anything, intrinsically if you look at the formula, well if I didn't have this r factorial, so if this factor here is missing, that's the permutations. So you can see immediately that if I scale by the factor r factorial, I reduce the number of permutations by that factor r factorial, and that happens to give you the number of combinations. Okay, so let's think about back to our example. Sorry, that was a deviation. So if we're not concerned with the order in which the 3 letters are chosen, the 4 letters A, B, C, and D, there are only 4 ways you can choose from those 3, and that was the first column. So each row, so again, if you've forgotten what row is, a row is this. So each row is basically the 3 factorial, 6 possible permutations of the letters. So why is that 6 factorial, 3 factorial? Why is that? Because here I've got 3 things and I want to know the number of permutations of 3 things. So that's 3 factorial, we already know that. So that's why they've got 6 along the rows. Okay. So basically the number of permutations 4 times 3 factorial is 4 factorial, as I said. So in general, there are r factorial permutations of r objects. We know that, we've already learned that. That's one of the first things that we did. So we select from a set of n objects. So n choose r is denoted as the number of ways of choosing r out of n objects, disregarding order. Okay, and we want to we want to understand the intuition for the formula that we gave. So then what we must have is the number of possible ways of choosing r out of n multiplied by the number of ways you can permute that is equal to the number of permutations. So what I'm trying to say is r factorial times this thing, it must be the number of permutations, precisely because if I choose n choose r, I get that's my combinations, and I multiply by that by r factorial, that gives me my number of permutations in total. Okay. Now, of course, I don't know the formula which I've highlighted in the second bullet point, but I do know the formula for the number of permutations, so I'm going to reverse engineering the formula. So that is why this n choose r, he uses this ncr, it's the same thing. This thing times r factorial must be equal to the number of permutations. Okay? So I know the number of permutations, that's n factorial divided by n minus r factorial. Now if I divide both sides by r factorial, I get precisely my formula for NCR. Okay? And that's my number of combinations. Do you mind, please? I want to... Sorry. Thanks. Okay, so that gives us the total number of combinations. Okay? And that's the formula. So basically, it's reverse engineering it. We know from the beginning the number of permutations is more than the number of combinations, or at least as many, right? And then basically, I know basically then I know that the number of permutations is equal to the number of combinations multiplied by the number of permutations of those R things I can take. And so then if I divide through by R factorial, I get the formula for the number of combinations. Sorry, I'm repeating myself. If that helps, I don't know if it does. Okay. All right, so we're almost finished for the lecture, so we've just got 7 minutes left, but I'll try and finish it as soon as I can. It's a lot of information to take on, but you have a week to recover from it. So that's called n choose r. It's called the binomial coefficient. Why is that the case? So I'm sure all of you study A-level mathematics at the very least. You did the binomial expansion, which is basically I take two real numbers, a and b. I take that to the power n. And if you work out the expansion, for that, for n an integer, you get the coefficient n choose r for the rth term in that power series. Okay, so that's why it's called a binomial coefficient. Okay, so the following formula, I guess, you can verify these yourselves. I really think this is at the level where it's relatively straightforward. We're going to use these formulas, that's why they're quoted. So you can show that n choose r is equal to n choose n minus r. R has to lie in the set 0 up to n. Okay, you can check that. How do you do that? Well, you know the formula for n choose r. That's n factorial over n minus r factorial over r factorial. So that's my left-hand side. My right-hand side is n factorial over n minus r factorial over n minus r factorial, which is r factorial. So this one is equal to this one. Okay. I'm sorry, you can replay that. I'm sure it's on video. You can play in slow motion or something. And you can do the same thing here. I mean, I don't really have to you can do exactly the same thing for these formula here. There are the constraint on R. R is in the set 1 up to n. And the final formula, n choose r is equal to 0. Well, basically that's a kind of convention. So strictly what we do is we choose r to be in the set 0, 1 up to n. If r is not in that set, by definition, we take the convention that n choose r is precisely equal to 0. Okay, this is just a notational convention. It just means that basically we don't compute quantities which don't make any sense. Okay, so we're almost finished. So let's just look at some examples and then we will break. So this is what I think is one example actually. So you have 25 good apples and you have 5 bad apples. Okay, and you take a sample of 5 without replacements. So I have my box of apples, I take out 5 apples. Okay, so now we are answering the questions, 3 questions, excuse me. How many samples can you select? How many of the samples in A involve exactly 1 bad apple? And how many of the samples in C include at least 2 bad apples? Okay, let's have a look. So let's look at example 1, part A. So part A, how many samples can you select? Okay, this is not so bad. So there are 30 apples, and you've got 5 apples. Okay. And basically now, I'm not interested in the permutation, right? If I take 3 bad apples and that's that's what I get. So basically I'm choosing 5 from 30, so the number of combinations I could do is 30 choose 5. Okay, 30 choose 5 has precisely this formula. Okay, so that's the first part. So now the part B says I have how many samples in A involve exactly 1 bad apple. Okay, this one's a little bit more challenging. So the number of ways a bad apple can be selected from one of the 5 bad ones is 5, if I choose 1. The number of ways of choosing 4 good apples is going to be from the 25 good ones is 25 choose 4. And so there are 2 groups in the sample, one group of bad apple, another group of bad apples, good and bad apples, sorry. So for each choice of the first group of bad apple, there are 25 choose 4 ways of choosing 4 good apples. So by the multiplication principle, I'm going to do 5 choose 1 times 25 choose 4. Okay, that's basically basically the logic is the multiplication principle. So we're combining 2 things we've learned today, the multiplication principle and combinations. Okay, part C. So I promised to finish this before the end of the lecture. So part C, how many of the samples in A involve at least 2 bad apples. So we really have to, we've selected the apples and now we've got to choose a case where there are at least 2 bad apples. Okay. So the number of samples, so at least 2 means 2, 3, 4, 5. Okay. So 2 is basically what we're doing is we're repeating part B in the case we have 2, 3, 4, and 5. So 2 was, so the case of 1 was 5 choose 1 times 25 choose 4. So the case of 2 is 5 choose 2 times 25 choose 3. The case of 3 is 5 choose 3 times 25 choose 2. The case of 4 is 5 choose 4 times 25 choose 1. I'm just repeating part B when you're replacing 1 with 2, 3, 4, and 5. Okay? And the case when you have 5 is 5 choose 5 times 25 choose 0, which is 1, unsurprisingly. And so the answer is, I add them all together, and that's my solution. Okay? That's exactly what you get. So you add them all together, that's those 4 numbers, 23,000, 3,000, 100, 25, 101, and that's the solution. Okay? And we don't have time to do example 2, so that's it for this week. So we'll resume on Thursday at 2 o'clock in LT26. Thanks very much for your attention.